We're going to do a few problems to review for the Chapter 4 test. So we're going to do some where we're going to get we'll look at the graph of the derivative and get the second derivative, and we'll also try to figure out how to get the original function from the derivative. And then we'll do an optimization problem and a related rates problem and a graphing problem. Okay, so here we have f prime, and we're going to try to get f double prime. I don't know why my pen is so faint here. I know that's hard to see, but it's not working well, and I don't know how to fix it, so we'll have to do the best we can until I can figure out whatever the issue is. So if we're trying to get the second derivative, then that means we want the derivative of this function. So we can see there's a horizontal tangent here. That's going to be an x-intercept in the derivative. Likewise, there's another horizontal asymptote right in here, and another horizontal asymptote, and another one here. Now, the function is increasing as we move along in here, so that means that the derivative of this function, which is what we're graphing, is going to be positive. So it's going to be positive until we get to here. And maybe I should make that, it's kind of hard to erase also. Don't know why this is so difficult, but I'm going to try to make it go more out to the edge of the graph. Okay, and then we're going to where this has its steepest point, where that has an inflection point, is where that derivative graph is going to be the steepest. So we can see the derivative is negative, a bigger negative, a bigger negative. That's going to be the biggest negative derivative. It'll continue being negative, but not quite such a big one. So where the inflection point is on the derivative graph is where the relative minimum is going to be on the second derivative graph. And then it's going to make its way up to here. And likewise, we can see that somewhere in this area is an inflection point, and that's going to be a relative maximum for our second derivative. And likewise, somewhere in this neighborhood is going to be our relative minimum. And somewhere in that area, let me get my pen back. So somewhere in this area, in this x value, is going to be our relative maximum, because that's where the inflection point will be. And then we're going to go negative, and somewhere in here, in this x value, is going to be our relative minimum. Then it's going to continue, it's going to approach horizontal, but always be decreasing a little bit. And so we're going to approach the x-axis from below. Okay, let's see what we can do now. I'm going to switch colors here. So now we're seeing the derivative, and we're trying to get the graph of the original function f. So where our derivative changes from positive to negative is going to be a relative maximum. Where it changes from negative to positive is going to be a relative minimum. We have no idea what the y values are. This is going to be a place where the derivative, where the function is going to have a horizontal tangent for a moment, but we can see that the derivative is going to go negative, 0, but then negative again. So that's going to be what we're going to call a shelf point, where we see our derivative has relative maxes and mins, are where our original function is going to have an inflection point. So these are going to be points of inflection. Okay, now we don't know what the y values are, so that could be different from one graph to another. So we're going to start out, and this is a little bit positive, so it's going to be increasing a little bit. it's going to get steeper and steeper and steeper until we get to this x value where we have that inflection point. Then it's going to continue to increase because our derivative is still positive until we get to this point, and then but it's now concave down. So we've got an inflection point, and now here's going to be our relative maximum. Now our derivative is going to be decreasing, so it's going to get steeper and steeper and steeper until we hit this inflection point. So somewhere in here, it's going to continue to decrease because our derivative is negative, but now it's going to be concave up until we hit this point where we get a horizontal tangent. So it looks like at this point it could be a relative minimum, but no, it's going to go back to decreasing again. So it's going to do that until we get to this place here where we have an inflection point. So that's its steepest negative right there. Now it's going to continue to be negative, so it's still decreasing, but now it's switched to concave up. Oh, look at that, I actually hit it. And so there is going to be our relative minimum right there. Now we're going to be increasing in here because our derivative is positive until we get to this place, which is going to be an inflection point. It's going to continue to increase, but it's going to sort of level off and approach some kind of horizontal tangent from below there, always still increasing a little bit. Those are tough. Let's look at the next panel. And here what we're going to do is number 11 on Miss Brown. So this is a really tough one because we're going to have a domain that is all real numbers. And so it's an open interval domain, and we're going to get more than one critical point. So it's as hard as it gets in terms of justifying what's going to be an absolute max or not absolute min. Now it's also tricky because we want to look at the tangent lines to this curve. That means we're going to look at the derivative to this to get slopes of tangents. Then we want to find the maximum and minimum slope. So we want to find the maximum and minimum of the derivative. So here's our first derivative, and that's going to be, let's go ahead and do a quotient rule. So we'll take our denominator times the derivative of the numerator, which is 0, minus our numerator times the derivative of the denominator, all over the denominator squared. So that's going to look like a negative 12x over x squared plus 3 quantity squared. So these are our slopes of tangent lines. These are what we want to find the largest and the smallest. So we're looking for an absolute maximum and an absolute minimum of this. So that means we're going to take its derivative. So now it gets a little more complicated. We're going to take our denominator using our quotient rule. So our denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, which is going to be a chain rule. So that's 2 times x squared plus 3 to the first times the derivative of the inside function 2x, and that's all over the denominator squared. Now we're looking for critical points here. So we want to know where is our derivative of the slopes going to be 0 or undefined. Well, the denominator is never 0, so we're not going to get anything from there. Let's do some factoring in that numerator. We can factor out an x squared plus 3, and I think we can also factor out a 12. So let's see what's left behind if we take out a 12 and an x squared plus 3. So we'll still have a negative from that negative 12. We'll still have an x squared plus 3. If we took out that 12, then we're going to have a 2x times another 2x is going to be a 4x squared, and we took out that other x squared plus 3. So we're looking at this. Now we can cancel that, although that's not really going to impact what we're doing a whole lot. And we want to set this equal to 0, which means we want the numerator to be 0. So if we factor out, let's see, we got 12, and then if we distribute that negative sign in there, that's going to give us a 3x squared minus 3, and we still have that x squared plus 3 to the third that we're trying to find where that's equal to 0. We can factor another 3 out of that numerator, which will leave us with an x squared minus 1. So things are taking shape now. So if x squared minus 1 is 0, that's the numerator. That means that x can be a positive 1 or a negative 1. So those are nice numbers to work with, but sadly there are 2 of them. That makes our life even more complicated. So now to make an argument that this is going to be, we're looking for the largest and the smallest of these slopes of tangent lines. So if we had a closed interval, we could do our candidate test and plug in the endpoints. Because they're open intervals and we have more than one critical point, instead of plugging in the endpoints, we're going to take the limit as x approaches the left endpoint of our original function and the limit as x approaches the right endpoint of our original function. And then I'm going to slide this up a little bit. We're also going to plug in -1 and +1, our critical points. And we're looking for the largest and the smallest. So remember, our function is actually this derivative, because this is where our slopes are coming from. So this is what we're plugging into, and this is what we're taking the limit of. So as x goes to negative infinity, this denominator here is going to be, actually this huge negative number is going to get raised to the fourth and only to the first there. So that means that this is going to go to 0. And similarly, as x goes to positive infinity, the power, the degree of the denominator is larger than the degree of the numerator, and so it too is going to go to 0. Now when we plug in -1, we're going to get -12 times -1 is going to be a positive 12. We'll get -1 squared is 1, plus 3 is 4, squared is going to be 16. That's going to be a positive 3/4. When we plug in a positive 1, we're going to get a -12 in the numerator, and we'll still get 16 in the denominator, and so we'll get -3/4. This is good news, because if either of our limits had been the biggest or smallest, then we would not have had an absolute max or an absolute minimum, because it's never going to actually reach that. But we can say that the maximum slope is going to be our 3/4, and our minimum slope is going to be the -3/4. And our work here serves as our justification, because that's a modified candidate test. That's about as hard as it gets on an optimization problem. Let's look at a related rates problem. Okay, so here we have water is leaking from an inverted conical tank at 3 cubic feet per minute. If the tank has a radius of 6 feet and a height of 12 feet, how fast is the water level falling when the water in the tank is 8 feet deep? So let's see what we know here. We know that the water is leaving the tank, leaking out at 3 cubic feet per minute. So that is going to be a rate of change of the volume. That's a derivative of the volume with respect to t. Since the volume is decreasing, we're going to call that a -3. We are looking for the dH dt. How fast is the water level falling? And we want this when the height is 8 feet. Now when you look at the water in the tank, you can see that the triangle formed here by the water is going to be proportional to, it's going to be similar to that triangle formed by the tank itself. And so in similar triangles, we know that the corresponding sides are proportional. So the r over 6, that's the radius in the small triangle of water over the radius of the big triangle in the tank, is going to be proportional to the height of the water over the height of the tank, or you could have done that any way you like. So if you want, you could also have said, and maybe this is an easier way of thinking of it, if I can erase, it doesn't erase very good. If we do maybe r over h is 6 over 12, which we can reduce to 1/2, we're going to get that r is going to be 1/2 h. So we can plug that into our volume formula. I meant to write that. Volume of a cone is 1/3 pi r squared h. So we can say V, before we take a derivative, I'm going to lump the 1/3 and the pi together as pi over 3. I'm going to replace that r with a 1/2 h, and that quantity is going to have to get squared. So the 1/2 gets squared and becomes 1/4. It can join the pi over 3 to become pi over 12, and the h squared times h is going to be h cubed. So now this is going to be much easier to take a derivative of, because I'm not going to have to do a product rule. So instead we'll get dv dt, the 3 times pi over 12 will become pi over 4, h to the second times dh dt. Now we can substitute in what we know. The dv dt we said was -3, and the h we said was 8 squared, and the dh dt is what we're looking for. So I'm going to try to make my life a little easier. So I'm going to look at that pi over 4 times, and I'm going to write that 8 squared as 8 over 8, so that I can cancel the 4 with one of those 8's. And so then we have -3 is equal to 16 pi times dh dt. So we'll get a -3 over 16 pi, and that's going to be in feet per minute for our dh dt. And so we can see that that water level is falling at 3 over 16 pi feet per minute. All right, let's see what the next one's going to be. Now we have a massive graphing problem. So we have y is equal to x squared over x minus 1, and we're going to get everything, all the information we can from the first derivative and the second derivative, and put it together and get as accurate a graph as we can. And we have a little hint that there's a slant asymptote there. So this has been a while. To get a slant asymptote, that happens when the degree of the numerator is 1 greater than the degree of the denominator. So we will long divide our x minus 1 into the x squared. So that's going to give us an x up here. X times x minus 1 is x squared minus x. We'll subtract that quantity. The x squareds will drop out. We'll get minus -x is a plus x. Then we'll say what times x minus 1 is going to equal x, and that's going to be a 1. So that will give us an x minus 1. We'll subtract that quantity, and that will give us a remainder of 1. So we will make that 1 over x minus 1. So this is equal to our original x squared over x minus 1. So if we look at the limit as x goes to infinity, then we can see that this remainder will go to 0, and our function will then look more and more like just x plus 1. So y equals x plus 1 is our slant asymptote. Okay, so we'll start the graphing process here. And we're going to see our slant asymptote is going to be y equals x plus 1. So I'm just going to go ahead and put that in blue. Everything is pretty faint here. So there is our slant asymptote. Okay, now let's see what information we can get from the first derivative. So dy dx, we can use a quotient rule here. So we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. We want to know where is that 0 or undefined. So it'll be 0 when the numerator is 0, and it'll be undefined when the denominator is 0. So if we look at that numerator, let's see, that'll be 2x squared minus 2x minus x squared. That's going to be over x minus 1 squared. So that's going to look like x squared minus 2x, I believe, over x minus 1 squared. So if we set the numerator equal to 0, we can see that that will be equal to 0 at 0 and 2. We also see that the denominator is 0 when x is 1. These are our critical points. So let's do a number line for the first derivative. And we're going to have 0 and 1 and 2. So to the left of 0, if we plug in -1, and I'm going to kind of look right here, if we plug in a -1, we're going to get -1 squared is 1, -2 times -1 is going to be a positive 2, so our numerator is positive, and our denominator is squared, so it's always positive, so it's going to be positive in here. If we plug in something like, say, 1/2, I think I'm going to look at the factored form of that numerator. Remember, that's x times x minus 2. So if I plug in a half, the x will be positive, but the x minus 2 will be negative. So we get positive times negative is negative. The denominator we said is always positive, so that's going to be negative. Now, when we plug in a positive half, then we'll have a positive where the x is. 1/2 minus 2 will be a negative. So we'll get a negative numerator over a positive denominator is also negative. And when we plug in something bigger than 2, then everything's positive, so we're back to being positive. So we can see that the function is increasing for x less than or equal to 0, and also for x greater than or equal to 2. The function is decreasing, and now we have to be a little careful here, because remember at 1, we've got a vertical asymptote. I should put that in there. We're going to have a vertical asymptote at x equals 1, because that's where that's going to be equal to 0 in the denominator. And so when we say it's decreasing, we're going to include the 0, but we aren't going to include the 1 because the original function is not defined there. And so we'll go from 1 to 2, including the 2, but not the 1. Now, we also can see that the derivative goes from positive to negative at 0, so we're going to get our relative max at x equals 0, and when we plug that into the original, we'll get 0 over -1 is 0, so 0, 0 is going to be a relative maximum, and we're going to get a relative minimum at x equals 2, because that's where our derivative changes from negative to positive. When we plug in 2 to the original function, 2 squared is 4, 2 minus 1 is 1, so that's going to be 2, 4. So at 2, 4, we're going to have a relative minimum. And we set a relative maximum at 0, 0. So there's our information from the first derivative. So let's go on and take the second derivative. See if I can slide this up a little bit. So we're going to now say the second derivative of y with respect to x. So I'm looking at this part right here, and it's going to get kind of messy. We're going to get our denominator times the derivative of the numerator. It's going to be 2x minus 2 minus our numerator, x squared minus 2x, times the derivative of the denominator, which is a chain rule derivative, and that's going to be all over our denominator squared, which is now up to the fourth power. So let's see if we can do some factoring here. I think we have an x minus 1, and I don't know. I think we can factor a 2 out of all of these as well. So let's see if we can pull out a 2 and an x minus 1. And I think that's about all we can do. So now this is the 2 times x minus 1 is actually this 2x minus 2 is what we pulled out. That's going to leave our x minus 1 squared still in the rest of this stuff. So we took the 2 and the x minus 1 out. So if we distribute that negative sign, that's going to be a minus x squared and a plus 2x. And that's all over x minus 1 to the fourth. We can cancel one of those x minus 1s. Let's see, we have 2 times. I think we're going to have to square out the x minus 1. That's first one squared, twice the product, plus the second one squared, minus x squared, plus 2x, still all over the x minus 1 cubed. So let's see. Looks like the x squareds will kill each other off. That's good news. So will the 2x's, even better. And so we're going to be left with just 2 over x minus 1 cubed. It's going to make our life a little easier in terms of looking at that second derivative, because the only pip is going to be 1. I put 0 down. That should be a 1. That's the only potential inflection point. And because that's to the third power, we can see if we put in something to the left, like 0, we're going to get a negative. And if we plug in something to the right, like say 2, it's going to be positive. So we can see that our original graph is going to be concave down for x less than 1, and it's going to be concave up for x greater than 1. And we have an inflection point, we would say at x equals 1, but remember that's our vertical asymptote. So there is no point on the graph there, so we don't get anything there. Well, let's see if we can put this together. So to the left of 0, we can see that it's going to be increasing and concave down. And we've got this asymptote. So our curve is going to be increasing and concave down until we get to 0. Then it's going to switch to decreasing and still be concave down as we approach that vertical asymptote. So it's going to look something like that. It's undefined at the vertical asymptote, so we hop over. Then it's going to be decreasing between 1 and 2 and be concave up. So we've got our vertical asymptote decreasing concave up, and then it's going to increase and continue to be concave up and approach that slant asymptote. And so there's a little different way of graphing this than we did in AP Prep.